Graphing logarithmic functions and transformations. Here is the parent function that we're going to start with, log base 2 of x. It doesn't matter what the base is. You can have a parent function for any base. And the critical point is 1, 0 for every logarithmic parent graph. And what we call the base point is at the base 1. So these are our two important points that we can use to graph any parent graph of a logarithmic function. Critical point is 1, 0. Base point at 2, 1. Okay. Everything that has to do, all of the attributes and key features of a logarithmic function are the inverse of those for exponential functions. Logarithms and exponentials are the inverse of one another. So we're going to see how this plays out and how each of the features are the opposite or switch in terms of x and y values. So for a logarithmic function, we will always have an x-intercept, and we call that the critical point. If it's a parent graph, regardless of the base for a logarithm, the critical point will always be 1, 0. The asymptote is a vertical asymptote, and this is located at x equals 0 for our parent graphs. All parent graphs for logarithms, no matter what the base, are going to have a vertical asymptote, and it will be an x equals line regardless of the transformations, and the parent graph will always be x equals 0. The curve looks like this, and the domain, we can see that when we are reading for domain, we always want to go from left to right, looking across the graph, looking to see where are the exclusions for the domain. And I can see that the left side of the graph, there are no values whatsoever. And in fact, this asymptote here is where my domain values begin. So the domain is going to begin at 0 and continue to positive infinity. The range, when I'm determining the range, I'm always going to look from bottom to top. I'm going to read my graph from the bottom going up, and I'm looking at what values are being used, what y values are being used in the range. There's no exclusions. There's no asymptotes of any kind. And so my range will always be all real numbers for all logarithmic functions. This graph is actually an increasing graph. This is the one feature that does not change between exponential and logarithmic functions. We say it's increasing if I look to the right side of the graph and my arrows are continually going up. So in other words, as my x values get bigger, what's happening to the graph? Is it going to continue to increase, or is it going to go down at some point? And in this case, it's going to continue to increase. So this is the one feature that doesn't switch. All the other key features have switched x and y in terms of the key features from an exponential graph. Transformational form, we're going to follow the same patterns that we have in the past. The main thing we're looking for is if it's negative. This will also determine a decreasing graph. If the a value is negative, that will give me a decreasing graph, and that will cause a reflection over the x-axis. We're not going to do any graphs that have stretches or compressions there, so strictly look for those reflections. The B value here, again, we're not going to do any horizontal stretches or compressions, but we are going to look to see if we get a negative in this position. If that happens, then I'm going to have a reflection over the y-axis. This is also referred to as a horizontal reflection. Then for our C value, it's the opposite of C. It's going to shift to the right or left. And it's always going to go in the opposite direction that my sign indicates. And our D value is going to cause our graph to shift up or down. Another piece of information that's useful is the fact that our C value is also going to determine our asymptote. Whatever that C value is ends up being my vertical asymptote for logarithm graphs, logarithm transformations. This here is a graph of, this is the graph of y equals log base 2 of x, like we just graphed up at the top of the page. This over here is the exponential graph of y equals 2 raised to the x power. And we see here that there's a reflection between these two. They are reflecting across this line here, which is the line of y equals x. And by definition, if that occurs, then we have inverses. So we know that these two graphs are inverses of one another based on the fact that they reflect across the line y equals x. Okay. On the next page, we have a little chart here to compare and contrast the exponential and logarithmic graphs. We have said already that the one feature that does not change between exponentials and logarithms is the fact that they are both increasing graphs. They're both increasing parent graphs. Both of them have increasing graphs for their parent graphs. A transformation of a reflection across the x-axis will cause it to be a decreasing graph. The critical point for exponentials is 0, 1. For logarithms, it's 1, 0. So notice how the x and y's switch places. The asymptote for exponentials is y equals 0. It is a horizontal asymptote, and logarithms have a vertical asymptote at x equals 0. The domain for exponentials is always going to be all real numbers, and it's the range of logarithms that is all reals. And then the range for exponentials is going to go from 0 to positive infinity, and that is actually the domain for logarithms. Okay, so taking a look at another parent graph, this one here, log base 4 of x, the critical point here is going to be 1, 0, the critical point for all parent graphs. And then the base point would be the base and then 1. The base of the logarithm here is 4. So the point 4, 1 would be my other point needed to graph. I have my logarithm curve, and my asymptote is here at 0. There are no transformations here. This is a parent graph. And anytime this base changes, I'm still going to have the same critical point. The base point will be different, but the same critical point, and it will just graph a different parent graph. The one right underneath is the natural log, and we've discussed in class that the base of the natural log is e. The little subscript is not written there, but it is an e. So my critical point is at 1, 0, and my base point is at e1, and e is approximately 2.718. So I can graph another parent graph, and same basic shape, just slight difference. Same asymptote here because this is another parent graph. Okay, so let's take a look at some transformations and how you're going to graph these on your assessment. When it comes to assessment day, you're not going to need to fill in this chart here for the parent function because we're going to rely on the calculator. So we do need to know what the parent function is, and it's going to be y equals the log of just x. Y equals log base 4 of x is my parent graph here. So any other numbers that have been added to my equation are going to cause transformations. That number is going to cause a transformation, and so is that one. And that's what they want me to list over here where it says transformations. The -3 here is going to cause my graph to shift to the right 3 units. And the +2 is going to cause my graph to go up 2. Since this is a log, my asymptote is going to come from this C value as well, and it's the opposite of that value. So +3 is going to be the asymptote. It's going to go through the x-axis at 3. X equals 3 is the equation of my asymptote. So I'm going to graph it by drawing a vertical dotted line through x equals 3. So from here, what we can do is rely on the calculator to tell us our critical and base points so we don't have to do any changes here. We want to type into the calculator this exact equation in the y equals screen. So go to your graphing calculator. Here we go. Y equals, and we had a log base 4. So I choose the math button and I arrow down to where I see log base. And then I type in log base 4 of x minus 3. Come outside the parentheses, add 2. Graph. I get a chance to see what the graph looks like. Remember, it doesn't stop there. It's only stopped there because the calculator doesn't have space to draw it. It gets so close to that asymptote at 3. And go to the table, so second table, and this is where I'm going to find my values to put into my table. We know that the asymptote's at 3, and so see how it says error here? The error is because of the fact that it's too close to calculate. It's so close to 3. But the other values here are going to help me. I'm looking for y values that are a whole number like this one. So 4, 2. is going to be one of my points, and then 7, 3 is another. 4, 2, the one closest to 0 is going to be your critical point. So 4, 2 is my critical point, and 7, 3 is my base point. So let's go back over here and plot our points. Draw my graph like I saw it on the calculator screen. It gets really close to the asymptote. I see that on the right side, my graph is continually going up. So this is going to be an increasing graph. The domain starts at 3, where the asymptote is, and goes to positive infinity. The range is all real numbers. Okay, let's do one more. This one underneath number 6 here has a reflection. So let's take a look at number 6. I don't need to fill in this table. I do need to know the parent function, and parent functions do not have any negatives in them. Remember, the parent function is where everything begins. A reflection is a transformation, so that negative symbol there is going to be one of my transformations. So let's mark all of those. I have that negative sign, I have a -1 and a +3. So I'm going to have a total of 3 transformations to list. The first one, the negative, makes my graph reflect over the x-axis. The -1 makes my graph go to the right 1 unit. And the +3 makes my graph move up 3 units. And then we also said the C value, this inside here, is going to tell me my asymptote. So my asymptote is going to be at x equals 1. And I'm going to go ahead and draw that dotted line through the x-axis at 1. And then I'm going to go over to the calculator and type in the function, type all of this into my calculator so I can take a look at the table and get my points. Okay, y equals, I'm going to clear that one out. Let's do math button. Go down until you see log base. We had a log base 2 of x minus 1 plus 3. And don't forget we have the negative in front. We have the negative in front of log. So I'm going to scoot all the way back here and insert my negative symbol, not subtraction sign, but the negative symbol. And let me double check and make sure I have the right equation. Negative base 2. Yes. Graph it. There we go. Okay, so this has flipped upside down. That reflection, that negative sign, we can see it happening. Let's go to the table. And my asymptote is at x equals 1. So it makes sense that it says error beginning with 1. That's the asymptote. So then these next 2 points are going to be my critical point and my base point. 2, 3, and 3, 2 are my critical point and base point. So over to up 3, over 3 and up 2. And I'm going to draw it the way it was shown on the calculator, like this, because it has flipped over. So this graph, we can see that as the x values get bigger, as I go out toward positive infinity, my x values are going to continually get larger, but the graph is going to continually go down. It's going to decrease. So this is a decreasing graph. We also knew that from the beginning because of the fact that we had the reflection over the x-axis. We knew that it should be a decreasing graph. So domain, I scan across my graph from left to right and look to see where the exclusions are. And my domain doesn't even start until I reach that asymptote at +1, and then it can go on all the way to infinity. The range, I need to scan my graph from bottom to top, and I'm looking for any exclusions. Now, we don't see anything down here in this bottom half of the graph, but you have to visualize that this graph is going to continually do this. And so eventually there will be values down here that are used. They're not restricted in any way. So range is all real numbers. That will always be the case. All the ranges for my logarithm graphs will be all reals.